Deep beneath the Swiss-French border, CERN's Large Hadron Collider has achieved something that honestly sounds like science fiction, creating conditions so extreme they may have briefly formed microscopic black holes. Now these aren't the massive cosmic devourers we know from space, but quantum-scale phenomena that exist for mere fractions of a second before evaporating in bursts of exotic particles. What scientists discovered in the aftermath of these experiments has, well, profound implications for our understanding of extra dimensions, quantum gravity, and the fundamental structure of reality itself. The theoretical foundation. The real secret behind microscopic black hole creation lies in some pretty cutting-edge theories about the nature of space itself. In standard physics, creating a black hole would require concentrating energy equivalent to around 10 to the 19th GeV, way beyond what any human-made machine could ever achieve. But theories involving extra dimensions like the Arcani-Hammett-Dimopoulos-Dvali or ADD model suggest that gravity might actually leak into hidden spatial dimensions while other forces stay confined to our familiar three-dimensional space. This would explain why gravity seems so much weaker than electromagnetic or nuclear forces. It's not inherently weak, but rather it's diluted across extra dimensions we just can't perceive. If this is true, it dramatically lowers the energy threshold for black hole formation, potentially bringing it within reach of the LHC's 13 to 14 TeV collision energies. The mathematical framework for these ideas really started to take shape around 1998 to 2000, when physicists like Nima Arcani-Hamed, Savas Dimopoulos, and Gia Dvali proposed that our universe might have more than the four dimensions we experience. These extra dimensions would be compactified, curled up so tightly at every point in space that we can't detect them in everyday life, yet they fundamentally alter how physics works at the tiniest scales. CERN's experimental setup. The Large Hadron Collider represents, honestly, humanity's most ambitious attempt to recreate conditions from the earliest moments of the universe. Built in a 27-kilometer tunnel beneath the Swiss-French border, the LHC accelerates protons to 99.9999991% of light speed before smashing them together with unprecedented energy. The ATLAS and CMS detectors, which are just massive instruments containing millions of sensors, capture the spray of particles created in these violent collisions. When protons collide at such extreme energies, they create conditions similar to those existing just a fraction of a second after the Big Bang, when temperatures exceeded 1,000,000 billion degrees. The detectors track every particle emerging from these collisions, always on the lookout for signatures of new physics beyond the standard model. The CMS, or Compact Muon Solenoid experiment, has been specifically searching for microscopic black hole signatures ever since the LHC's early runs. These searches focus on identifying the distinctive particle showers that would result from black hole evaporation through Hawking radiation. The detectors have to distinguish between ordinary particle collisions and the unique signatures that would indicate spacetime itself has temporarily collapsed into a microscopic black hole. The search for microscopic black holes. The CMS collaboration has, conducted extensive searches for microscopic black hole production throughout the LHC's operational history. During the 2010 run at 7 TeV center of mass energy, scientists analyzed proton-proton collision data, looking for the distinctive signatures that would indicate black hole formation and subsequent evaporation. According to theoretical predictions, if microscopic black holes formed, they would immediately evaporate through Hawking radiation, producing a characteristic spray of subatomic particles. These particles would create specific energy patterns detectable by the CMS detector's sophisticated sensors. The evaporation process would happen in about 10 to the minus 27th seconds, an almost incomprehensibly brief moment. The search parameters focused on black hole masses ranging from 3.5 to 4.5 TeV, based on various theoretical models involving extra dimensions. Scientists looked for events where particles emerged in patterns consistent with black hole decay, including high-energy jets and unusual particle multiplicities that just wouldn't occur in standard particle collisions. While no definitive evidence for microscopic black holes has been confirmed in peer-reviewed publications, the searches have provided valuable constraints on theoretical models and continue to refine our understanding of what might be possible at these extreme energy scales. Stephen Hawking's encouragement. In 2009, renowned physicist Stephen Hawking visited CERN's underground facilities and made a remarkable statement that really captured the scientific community's imagination. While touring the Atlas detector with CERN Director General Rolf Hoyer, Hawking expressed his hope that the LHC would successfully create black holes, saying with characteristic enthusiasm, "I hope you'll make black holes." This wasn't just scientific curiosity. Hawking understood that creating microscopic black holes would represent a fundamental breakthrough in physics. Such an achievement would provide the first experimental test of quantum gravity, the long-sought theory unifying Einstein's general relativity with quantum mechanics. It would also offer direct evidence for extra dimensions and validate decades of theoretical work. Hawking's encouragement came despite ongoing public concerns about LHC safety. A lawsuit had actually been filed in the United States expressing fears that the collider might create dangerous black holes or exotic matter that could destroy Earth. The lawsuit was eventually dismissed on grounds that speculative fear of future harm does not constitute an injury in fact sufficient to confer standing. Hawking's support helped legitimize the scientific importance of these experiments, emphasizing that any microscopic black holes created would evaporate instantly through the radiation process he had theorized decades earlier. The Hawking radiation process. The theoretical framework for microscopic black hole evaporation relies on Stephen Hawking's groundbreaking work from the 1970s, which showed that black holes aren't completely black, but emit radiation through quantum effects at their event horizons. This process, known as Hawking radiation, happens because quantum mechanics allows particle-antiparticle pairs to spontaneously appear near the black hole's boundary. In this process, one particle from each pair falls into the black hole while the other escapes, carrying away energy and causing the black hole to gradually lose mass. For microscopic black holes, this evaporation happens almost instantaneously. The smaller the black hole, the faster it evaporates. A black hole with the mass of a proton would disappear in about 10 to the minus 27th seconds. The evaporation produces a distinctive signature, a burst of particles with specific energy distributions and correlations. These particles would include photons, electrons, muons, and potentially exotic particles not found in the standard model. The exact composition depends on the black hole's mass and the number of extra dimensions through which gravity can propagate. This rapid evaporation is crucial for safety. Any microscopic black holes created at the LHC would disappear before they could interact significantly with surrounding matter, making them scientifically fascinating but, practically harmless. Recent experimental developments. In 2024, CERN's High-Radmat facility achieved a significant breakthrough by creating high-density electron-positron plasma beams that mimic the jets of matter and antimatter streaming from astrophysical black holes. The Fireball collaboration, led by researchers including Gianluca Sari, successfully produced plasma containing around 10 trillion electron-positron pairs, the highest density ever achieved in laboratory conditions. This experiment doesn't create actual black holes, but it recreates the extreme plasma conditions found in black hole jets, providing insights into how these cosmic phenomena behave. The research helps validate theoretical models of black hole physics using real experimental data rather than just computer simulations. Meanwhile, the search for actual microscopic black holes continues with increasingly sophisticated analysis techniques. Machine learning algorithms now scan collision data for subtle patterns that might indicate black hole formation and evaporation. These AI systems can detect correlations in particle tracks that human researchers might easily miss, potentially revealing evidence of quantum gravitational effects. The CMS and Atlas collaborations continue refining their search strategies, looking for soft, unclustered energy patterns. Subtle energy signals that don't form clear particle groups, but might indicate interactions with hidden dimensions or exotic physics beyond the standard model. Implications for extra dimensions. So, the search for microscopic black holes represents more than just an attempt to create exotic objects. It's actually a direct probe of spacetime's fundamental structure. If these black holes can be created at LHC energies, it would provide the first experimental evidence for extra dimensions beyond the three spatial dimensions we experience every day. The existence of extra dimensions would totally revolutionize our understanding of physics, and could explain why gravity appears so much weaker than the other fundamental forces. It would also suggest that our familiar three-dimensional space is just a brain embedded in a higher dimensional reality, with gravity able to propagate through the full multidimensional space, while other forces remain confined to our brain. Different theoretical models predict different numbers of extra dimensions, from one additional dimension in some scenarios, to 6 or even more in others. The energy threshold for black hole creation, and the characteristics of their evaporation, would reveal crucial information about these hidden aspects of reality. And, such discoveries would also have profound implications for cosmology, potentially explaining dark matter and dark energy as manifestations of physics operating in extra dimensions. So, the microscopic black holes created at CERN might provide the first laboratory window into these cosmic mysteries. Safety considerations and natural experiments. So, before launching any high-energy experiments, CERN scientists, really took their time with extensive safety assessments, especially when it came to concerns about microscopic black hole creation. The main argument for safety actually comes straight from nature. Cosmic rays are constantly bombarding Earth's atmosphere with energies that, honestly, far exceed anything the LHC could ever produce. Ultra-high-energy cosmic rays can carry energies up to 10 to the 20th power electron volts, which is, wow, about 10 million times higher than the LHC's maximum energy. These particles have been creating natural collisions with atmospheric nuclei continuously, and Earth has experienced roughly 1 million of these impacts per square kilometer every year for its entire 4.5 billion-year history. If microscopic black holes posed any danger at the energies CERN explores, nature would have already run these experiments countless times over. The simple fact that Earth is still here shows that any black holes created at these energy scales either evaporate harmlessly through Hawking radiation, or are just way too small to interact significantly with ordinary matter. And even if Hawking's theory turned out to be wrong and microscopic black holes didn't evaporate, they'd still pose no threat because of their incredibly weak interaction with normal matter. Such objects would just pass through Earth almost without any effect, kind of like the trillions of neutrinos that pass through our bodies every second without us ever noticing. Future prospects and upgraded searches. Looking ahead, as the LHC keeps running with upgraded detectors and higher luminosity, the search for microscopic black holes is, becoming more and more sophisticated. The high-luminosity LHC, which is expected to start up in the late 2020s, will actually provide 10 times more collision data, and that will dramatically improve our sensitivity to rare phenomena. Future experiments are going to use advanced artificial intelligence to analyze all that collision data, searching for subtle patterns that could hint at black hole formation. These AI systems can process vast amounts of data at the same time, spotting correlations and anomalies that would honestly be impossible for human researchers to catch manually. Then there's the proposed Future Circular Collider, a 100-kilometer ring that would operate at much higher energies than the current LHC, which could, in theory, give us a definite answer about microscopic black hole production. Running at energies up to 100 tera-electron volts, this facility would probe energy scales where extra-dimensional effects should, become really clear. Beyond just searching for black holes, these experiments keep pushing the boundaries of fundamental physics, seeking evidence of things like supersymmetry, dark matter particles, and other phenomena that could totally revolutionize our understanding of the universe. Every single collision gives us new data about the deepest levels of reality. The quest for quantum gravity. The quest for quantum gravity is really at the heart of this search for microscopic black holes. It's humanity's most direct attempt to probe the elusive theory that would finally unify Einstein's general relativity with quantum mechanics. Creating and studying these tiny objects would, for the first time, give us experimental data on how gravity behaves at quantum scales. These experiments could help resolve some of the most fundamental paradoxes in physics, like the black hole information paradox that's puzzled scientists for decades. If we can create microscopic black holes and study their evaporation in detail, it might finally tell us whether information falling into black holes is truly lost, or if it's somehow preserved in the radiation they emit, and the implications go way beyond just academic physics. Understanding quantum gravity could potentially unlock new technologies based on manipulating spacetime, maybe even leading to advances in energy generation, transportation, or our understanding of consciousness itself. The microscopic black holes created at CERN might actually be the first steps toward a truly unified theory of everything. As scientists keep pushing the boundaries of what's possible, each experiment brings us a little closer to answering the deepest questions about the nature of reality, and whether or not microscopic black holes have actually been created. The search itself has already advanced our understanding of the universe's fundamental structure. So in the end, the quest to create microscopic black holes at CERN is really about more than just scientific curiosity. It's humanity's attempt to probe the deepest levels of reality itself. Whether these quantum-scale phenomena have been successfully created or, still remain tantalizingly out of reach. The search has already revolutionized our understanding of space-time, extra dimensions, and the fundamental forces that govern our universe. As technology keeps advancing and new experiments push ever deeper into the quantum realm, we're edging closer to answering the ultimate questions about existence itself. The universe's deepest secrets may finally be within our grasp.